In this video, we will discuss how molecular geometries are rationalized by the hybrid orbital model, how to identify hybridization of atoms in a molecule, and the interactions between different orbitals that form bonds. In the last video, we discussed that a carbon atom bonded to four separate groups has a tetrahedral geometry with bond angles of approximately 109.5 degrees. But as we saw, carbon isn't always bonded to four separate groups. Understandably, carbons in alkenes and alkynes have different molecular geometries and bond angles than tetrahedral carbons in alkanes. Let's start by unpacking the reason why different molecules adopt certain geometries with specific bond angles. We can start with methane, a molecule with a tetrahedral carbon center. As you may already know, electrons are negatively charged, and like charges repel. In a tetrahedral carbon, 109.5 degrees is the orientation that maximizes the distance between each of the four bonding pairs, minimizing their repulsive interactions. Effectively, a molecule's geometry is a direct consequence of the repulsion of its electron domains, or regions of electron density, around the central atom. With this in mind, let's discuss how we describe the orbitals used to give these specific bond angles. For this, we can employ the hybrid orbital model using the same example. Here's what the hybrid orbital model tells us. None of the bonding orbitals in a tetrahedral carbon are 100% s or 100% p. Rather, they are hybrid orbitals that have partial s and partial p character. Carbon's three 2p orbitals and lone 2s orbital hybridize, or blend together, to create four sp3 orbitals, which are positioned tetrahedrally around the carbon atom. Each of these four sp3 hybrid orbitals has 25% s character and 75% p character. In the case of methane, CH4, each of the sp3 hybrid orbitals overlaps with a 1s orbital from hydrogen to form the four CH sigma bonds. This sp3 hybridization isn't unique to just methane and applies to any situation where a first-row element is bonded to four atoms. For example, the nitrogen in ammonium and boron in borohydride are sp3 hybridized. Moreover, the tetrahedral orbital arrangement also holds for central atoms where one or more pairs of electrons is a non-bonding pair. For example, the nitrogen in ammonia has four electron pairs with three electron pairs that participate in bonding and one pair of non-bonding electrons. The ideal geometry for arranging four pairs of electrons is tetrahedral. Therefore, we still call the nitrogen sp3 hybridized. However, although the orbitals still adopt the tetrahedral arrangement, we refer to the molecular geometry of these molecules as trigonal pyramidal. In molecules with a trigonal pyramidal geometry, such as NH3, the bond angles are compressed from the ideal 109.5 degrees to around 107 degrees. This is because non-bonding electron pairs are more repulsive than a standard bonding pair, as the electrons are closer to the central atom. Deviation from ideal bond angles is even greater in molecules with central atoms that have two non-bonding electron pairs, such as in oxygen and water. So while the orbital geometry is still tetrahedral, and we therefore still call the oxygen sp3 hybridized, the molecular geometry is called bent. Now suppose that we mix the 2s orbital with only two of the 2p orbitals. It doesn't matter which 2p orbitals we pick. I will just pick px and pz. This would give us three sp2 hybrid orbitals with 33% s character and 66% p character, as well as one leftover unhybridized p orbital. When electron pairs occupy the three sp2 hybrid orbitals, the bond angle that maximizes their distance apart is 120 degrees. These bond angles result in a trigonal planar arrangement of the sp2 hybrid orbitals with the unhybridized p orbital perpendicular to the plane. Recall that each of the three 2p orbitals, px, py, pz, are right angles to each other. The two orbitals that are hybridized, say px and pz, lie in the plane, while the remaining orbital py is perpendicular to the plane. Methyl carbocation is an example of a trigonal planar molecule with sp2 hybrid orbitals. In the case of carbocations, the unhybridized p orbital is empty, which gives the carbon its plus charge. sp2 hybridized atoms are also in molecules with double bonds, such as alkenes. If adjacent atoms have single electrons in unhybridized p orbitals, and these orbitals are allowed to overlap, a pi bond is formed. The carbons in ethylene and carbon and oxygen in formaldehyde are all sp2 hybridized and exhibit pi bonding. It's important to remember that sp2 hybrid orbitals can also house non-bonding electron pairs, as in the case of the carbonyl oxygen, which has two non-bonding electron pairs in two sp2 hybrid orbitals. Finally, suppose that we mix the 2s orbital with only one of the 2p orbitals. This would give us two sp hybrid orbitals with 50% s character and 50% p character, as well as two leftover unhybridized p orbitals. These sp hybrid orbitals are separated by the maximum angle of 180 degrees, and we refer to this molecular geometry as linear. The two unhybridized p orbitals are each positioned at a right angle to the sp hybrid orbitals. Sp hybridization is most commonly observed in situations where a single atom forms two pi bonds or a triple bond. For example, in alkynes and nitriles or CN groups, the carbons and nitrogen are all sp hybridized. Just as with the other hybrid orbitals, sp orbitals can house non-bonding electron pairs, as seen with the electron pair on nitrogen in a nitrile. Now that we've covered the important topics, here is a shortcut that you can use to determine hybridization quickly. Add the number of atoms and non-bonding electron pairs attached to the atom you want to determine the hybridization of. If atoms plus non-bonding electron pairs equals 4, the central atom is sp3 hybridized. If the sum is 3, the central atom is sp2 hybridized, and if the sum is 2, the central atom is sp hybridized. Let's apply this shortcut to examples we've seen. Methane is tetrahedral, so we call the carbon sp3 hybridized. 4 attached atoms plus 0 non-bonding pairs equals 4, so sp3. We know the double-bonded carbon atoms in an alkene are sp2 hybridized. 3 attached atoms plus 0 non-bonding pairs equals 3, so sp2. Finally, we know the triple-bonded carbon atoms in an alkyne are sp hybridized. 2 attached atoms plus 0 non-bonding pairs equals 2, so sp. It's important to note one key exception to this rule: atoms with non-bonding electron pairs adjacent to pi bonds. We will discuss the reason for this exception more in detail in a later video. The last thing we will cover in this video is the different types of sigma bonds. Recall that pi bonds are formed by unhybridized p orbitals that align in the same plane, so there is really only one type of pi bond. Sigma bonds, however, are formed by orbital overlap, so there can be multiple types of sigma bonds, namely these 6 shown in the examples in red. sp3-sp3 sigma bonds, shown in ethane, sp3-sp2 sigma bonds, shown in propylene, sp3-sp sigma bonds, shown in propyne, sp2-sp2 sigma bonds, shown in 1,3-butadiene, sp2-sp sigma bonds, shown in but-1-ene-3-wyene, and sp-sp sigma bonds, shown in 1,3-butadiene. A general rule is the more s character a bond has, the more tightly it will hold the electrons in the bond. This applies to relative bond strengths and explains the reason why sp-sp sigma bonds are stronger than sp3-sp3 sigma bonds. Let's do some practice. Identify the molecular geometry and hybridization of central atoms in the molecules below. Feel free to pause the video and try these problems on your own first. Although many of you may not be familiar with dimethyl ether, its structure resembles water if the hydrogens were replaced with CH3 or methyl groups. We can start by determining the hybridization of the carbons in the methyl groups first. Both carbons are bonded to 4 separate groups, 3 hydrogens and an oxygen. The ideal geometry for arranging 4 bonding pairs of electrons is tetrahedral. Therefore, we would consider the carbons in both methyl groups to be sp3 hybridized. Using the shortcut gets us to the same answer. Each carbon has 4 atoms bonded to it and 0 non-bonding pairs. The sum is 4, so the carbon is sp3 hybridized. Now we can turn our attention back to the oxygen. To assign the proper hybridization to oxygen, we first need to recognize hybridization ambiguities. At first glance, because dimethyl ether so closely resembles water, we would assume the oxygen atom has a tetrahedral orbital arrangement and is sp3 hybridized. This is indeed correct. When drawing the sp3 hybrid orbitals housing the 2 non-bonding electron pairs, the structure of dimethyl ether would look like this. In this drawing, the 2 methyl groups point out of and into the plane of the paper, with the 2 remaining sp3 orbitals housing the non-bonding electron pairs. This depiction illustrates the tetrahedral orbital arrangement that confirms the oxygen is sp3 hybridized. However, it is also possible to draw dimethyl ether like this. This drawing depicts dimethyl ether as trigonal planar, where all three sp2 hybrid orbitals that form bonds with the two methyl groups and house the one pair of non-bonding electrons lie in a plane, with the unhybridized p orbital perpendicular to the plane housing the second pair of non-bonding electrons. As a result, it is hard to unambiguously assign the hybridization of dimethyl ether as only sp3 or only sp2, and we call the oxygen sp3 or sp2 hybridized. Before returning to the rest of the practice problems, let's quickly discuss how to determine the hybridization of oxygen atoms in four situations. Situation 1 is when an oxygen atom is bonded to two other atoms, like in dimethyl ether. In this case, the oxygen atom can assume either sp3 or sp2 hybridization as we just described. Situation 2 is when an oxygen atom is bonded to three other atoms, as in protonated dimethyl ether. The oxygen atom has a positive charge because it is bonded to more than two groups, and the only hybridization that fits is sp3 because the molecule is non-planar, and hence oxygen cannot be sp2 or sp hybridized. Situation 3 is when an oxygen atom is bonded to only one other atom, as in methoxide. In this situation, the oxygen atom can be sp3, sp2, or sp hybridized. Here are the orbitals drawn that support this ambiguity. Finally, situation 4 is when an oxygen atom is doubly bonded to one other atom, as in formaldehyde. Here are the orbitals drawn that support this ambiguity. Now let's go back to the practice problems. In hydrazine, both nitrogens are bonded to three separate atoms and have one pair of non-bonding electrons. When we draw out the molecule with stereochemistry, each nitrogen center resembles the nitrogen center in ammonia, NH3, which we know has a trigonal pyramidal geometry and is sp3 hybridized. The overall molecular geometry is therefore a staggered arrangement of the two trigonal pyramidal nitrogen atoms connected by the single NN bond. In triethylamine, the central nitrogen is bonded to three separate ethyl CH3CH2 groups and has one pair of non-bonding electrons. This nitrogen center also resembles the one in ammonia, NH3, which we know has a trigonal pyramidal geometry and is sp3 hybridized. All the carbon atoms in the molecule are bonded to four separate groups, giving them a tetrahedral geometry and making them sp3 hybridized. In ethanone, the N carbon is bonded to two hydrogens and doubly bonded to the center carbon. This carbon resembles a carbon participating in pi bonding in an alkene, which has a trigonal planar geometry and is sp2 hybridized. The center carbon is doubly bonded to both the N carbon and the oxygen, giving it a linear geometry and sp hybridization. Finally, the oxygen atom once again has some hybridization ambiguity. We observe that the oxygen forms a pi bond with the center carbon. Recall that pi bonds are formed by unhybridized p orbitals with lone electrons that align in the same plane, so this tells us the oxygen has at least one unhybridized p orbital that can participate in pi bonding. This rules out sp3 hybridization, where all of the p orbitals have been hybridized, leaving sp2 and sp hybridization as possible candidates. In this case, it's hard to unambiguously assign one hybridization over the other because both are equally possible. If the oxygen atom were sp2 hybridized, the carbon and oxygen would form an sp-sp2 sigma bond with the lone electrons in the aligning unhybridized p orbitals forming the pi bond. The two non-bonding electron pairs on the oxygen would be housed in the remaining two sp2 orbitals that are not involved in bonding. Likewise, if the oxygen atom were sp hybridized, the carbon and oxygen would form an sp-sp sigma bond, with the lone electrons in the aligning unhybridized p orbitals forming the pi bond. In this case, the two non-bonding electron pairs on the oxygen would be housed in the remaining sp hybrid orbital and the other unhybridized p orbital. Both molecular geometries and hybridizations fit this part of the molecule, hence we call the hybridization of the oxygen atom sp2 or sp. Finally, let's look at N-methyl hydroxylamine. We've seen methyl groups in previous examples where we know the carbon center is tetrahedral and is sp3 hybridized. We've also seen a nitrogen center with a pair of non-bonding electrons bonded to three separate groups in previous examples. The nitrogen in N-methyl hydroxylamine resembles the nitrogen in ammonia, which has a trigonal pyramidal geometry and is sp3 hybridized. Finally, the oxygen in the hydroxyl group falls in situation 1 from our aside earlier, where an oxygen atom is bonded to two groups. As a result, we call the oxygen sp3 or sp2 hybridized. Let's move on to the next question. For each of the following bonds in ethanone and N-methyl hydroxylamine, indicate what atomic orbitals or hybrid atomic orbitals interact to form the bonding molecular orbitals. Again, feel free to pause the video and try these problems on your own first. For ethanone, we determined that the N-carbon is sp2 hybridized. Therefore, the carbon-hydrogen sigma bond is between the sp2 orbital of the carbon and the 1s orbital of the hydrogen. We also determined that the center carbon is sp hybridized. Hence, the carbon-carbon bond is an sp2-sp sigma bond with two aligning p orbitals forming the pi bond. Lastly, the carbon-oxygen bond is an sp-sp2 or sp-sp sigma bond with the two aligning p orbitals forming the pi bond. For N-methyl hydroxylamine, we determined that the carbon in the methyl group is sp3 hybridized. Therefore, the carbon-hydrogen sigma bond is between the sp3 orbital of the carbon and the 1s orbital of the hydrogen. We also determined that the nitrogen is sp3 hybridized, so the nitrogen-carbon bond is an sp3-sp3 sigma bond. The sp3 hybridized nitrogen is also bonded to a hydrogen and a hydroxyl group. The nitrogen-hydrogen bond is an sp3-1s sigma bond, and the nitrogen-oxygen bond is an sp3-sp3 or sp3-sp2 sigma bond. Finally, the oxygen-hydrogen bond is an sp3-1s or sp2-1s sigma bond. As always, thank you for watching, and I'll see you next time.